remember what I talked about. So the idea of Hough transform is that like sometimes you have an image and you have a lot of different shapes here and there, and you just want to kind of like detect those shapes there. So I'll give you an example. Let's say I have something prepared. So for example, if you look at the end result, something like that. Like I have an image here, and I try to detect some of the lines here. So it didn't detect all the lines, but it detects some of the lines here. So the way to do it, like one way you can think of like how to do it is like you're just trying to fit all the lines in the image, right? So basically you start with, for example, the image like this. And then, as usual, like you can just, if it's not grayscale, change it to grayscale, and then you can use a edge detector, for example, to detect edge, right? So, for example, just candy edge detector, find the edges as we discussed like in earlier lectures. So afterward, like one way you can do like after edge detection, this is basically just a binary image, right? Just 0 and 1. So you can think of like, okay, I just try to fit all different kind of lines here on this image. So and for example, like you think of I have something like whatever this image here. I don't know what is this. Maybe a pen. I don't know. Or like okay, more like a pen here. And I will just try different lines. So, for example, think of, okay, I try this line here, and then along this line, I count number of pixels I fall in this line, and then I try different lines, and again, I count the number of pixels fall in these lines, and I repeat and repeat and repeat. So eventually, like, I may find these lines that have most number of pixels falling on these lines, and then I say, okay, so I find this line, something like that. But as you can see, of course, over this image, there are lots of possibility of lines, right? So then, like you can take lots of compute to find some, not all the lines, just some of the lines here. So Hough transform is just a very kind of say a little bit careful way to do this. So what it's going to do is basically, if you think of any lines here, for example, you start with an image again. If you think of a line in the image, you can always parameterize the lines this way. So what I mean by parameterize is like if I have a line here, you can think of like this line using two parameters to describe this line. One is like the distance, maybe I use a different color here. The distance of this line between from the origin, basically the minimum distance of origin from this line here. So this is a right angle here. So this may be a distance here, call it d. And then like also like you can have an angle here, right? So the angle theta, or like you can think of the slope also. I guess theta is more intuitive. The theta and this d will basically, like, if I have these two parameters, will describe all the possible lines in this image, right? So given another example, maybe this is like, this d is like, this is equal to 5, and this theta is 45 degrees. Then I have another line that is basically, d is equal to maybe like 4, and then like theta is equal to 0. Then basically will correspond to a line something like this, right? So theta is 0, and like use this color again, maybe use green. So this is like 4, distance of 4, and then this theta is 0. So therefore this will correspond to a line something like that. So this is another line. and this line is correspond to these parameters. So now what we can do is that basically what Hough transform did is you just look at each of the pixels, or like each of the non-zero pixel after edge transform, edge detection. That, like, for example, this is the image after edge detection, that I have these outlines here, and I look at each of these non-zero pixel here, and then I think of like what is the lines, possible lines going to or like what is the lines to include this point here. So basically I will have all these lines here will be possible to include this point here, right? And so if I kind of map these lines here into this D and theta space here, that will correspond to something like, if now this is like the image space, right? I can consider a space something like called D and theta space, or maybe more typically maybe theta to D space maybe. So then have a point here will, if I look at all the different theta, for example, like I start with theta equal to 0. Theta equal to 0 will correspond to a line that is perpendicular, right? I will have a line something like that, right? This is theta equal to 0. Maybe I use another color, okay? This is theta equal to 0 going through that. So that will be theta equal to 0, and the D there will be, let's say this D is maybe 3. Then I will have in this line here in the D theta space, or the Hough transform space, will correspond to a point something like that, right? That is the line for this one. And then I can continue to change this theta, right? I can increase this theta. Then if I increase this theta a little bit, let's say this 5 degrees here, then as you can see the corresponding new lines, I'm sure like it's very hard to see, but the corresponding new lines will be something like that, right? And it looks like the distance now will be a little bit bigger. Maybe the D now is equal to 3.2, something like that. Then I have another point here, like from this is originally 0 here. Then I have a point here is correspond to degree 5 degree. That is like here this value is 3.2, something like that. So then as you can see, like I can keep changing this theta, and I can like just have a curve here correspond to all the lines. Again, use a different color. All the lines that fall into this point. So basically, you will have something similar to what I show here. So for example, I have this is like just one point here. If you look at the Hough transform there, you will have a line something like that. So okay, of course okay, maybe I don't show as a mesh. Maybe I show image show that. I didn't want this actually. I probably need to want this. It's a little bit slow because the MATLAB kernel is typically pretty slow. Yeah, we'll have something like that basically. So that's correspond to the Hough transform of this point here. So now I can repeat this. Let's say if I have another point here, then I compute the Hough transform again, then I'll have something like that. 2 lines here. I'm not sure it's easy to see, but if not, then it will be that correspond to. So anyway, I think you get the idea. So I have another point. Let's say I have another point here. I'll have like Hough transform like this way. So eventually, as you can see, if I build the entire line, let's say if I have the entire line there, I didn't have it here, then I basically will have peak here. Maybe I can even do it here, maybe. So if I have the, let's say I have what do I have here? I call the thing BW, yes. So I have BW, let's say, the entire row is equal to 1. Let's say I have my own image source file just to make it look that bigger. Let's see. So that's, let's say I have the entire line here. Now if I compute the Hough transform of that, so lots of typo. Maybe, yeah, it's better to match it. It's more clear, I guess. So then, oh, what? Oh, okay, yeah, because, okay. So you can see now, like, it's very clear. Then you have a peak that basically corresponds to the line of this line here. So, and that's how basically Hough transform work. I didn't spend much time, honestly. And this is another example, let's say, that I showed you earlier, that if I have an image like this, then I just, if I do a tiny detector, edge detector for that, I have this edge image. Then I compute the Hough transform. Then I will have lots of, like, kind of like curves that correspond to different pixels, different non-zeros in the image, right? And then like you just look for the peaks there that will correspond to the lines, and then like you have the lines there. Then basically with MATLAB you find the finding the peaks, and then you can display it like here. So, but the idea I want to say like is quite generic, because when you think of this, like you have these things here, you convert the image space into a Hough transform space, in particular for these lines here, like with parameter like theta and d. And you can think of like different shapes. Just for example, like I can think of circle here, all the different circles in the image. And I can also parameterize all the circles in the image, right? So basically a circle in an image will be just, you can think of like completely defined by just a center of the circle and also the radius, right? So therefore there will be like just 3 parameters here. So you have like, let's say the XO, YO, and then radius. And again, you can do exactly the same thing. You can just look for, for example, you have an image here. You look for all the pixels in the image, and then that will correspond to a curve now in a three-dimensional Hough transform space. And afterward, again, you can find the peak there, find the maximum there, that will correspond to the circles there. The only issue here is like, actually, this direct implementation is not very typical, because if you think of that, like when you go beyond lines, you have quite a few of parameters, and then like this matrix alone is pretty big, and even you ignore the space consumption here, there will be lots of compute to do this. So one modification is like you can do so-called like randomized or like probabilistic Hough transform. So instead of for each of the pixel, you compute the corresponding curve in the Hough transform space. Maybe you just randomly pick pixels, or like in some cases, for example, for circle, you can randomly, instead of just pick one pixels there, you can pick like multiple pixels, right? For example, like I can pick like 3 pixels here. That's like 3 non-zero values here. That will kind of immediately specify the circle. Of course, it will lead to some kind of computations here. Or like you can go log as extreme for this, like extreme in the sense that you need to solve this. Basically, if you do this, then you are solving all some kind of like geometric equation here. But for example, I can just pick 2 points here, right? For example, for this circle here, I pick 2 points. So for 2 points, then I can think of, okay, for these 2 points, what kind of circles can include these 2 points here? That will be basically circle that with the center pass through the line here, right? Something like that is equidistant from these 2 points here. Right? For example, like I can have all the center that fall on these lines, for example, the center here, and the radius can be easily computed as the distance between like this point here from any of these chosen points here. So I will have now radius is here, and basically the location here will basically pick this like x naught, y naught, something like that. And then again, like you will in the Hough transform space, if you pick 2 points here, you basically will generate a line in the Hough transform space. But then like, of course, like the Hough transform space for the circle is actually 3-dimensional. So you have a line in a 3-dimensional space. Then you will have like, you randomly pick points here again, like, and you continue to do that, then you will overlap lots of lines in the 3-dimensional space. And then again, you're trying to find the peak there, and then you'll find the circles there, the circle there. And actually, I have another example is exactly using this method. Let me, because this uses lots of computation. So this is an example that basically I have some coins here. So and maybe I just want it anyway, or maybe I don't need to want it. But so as you can see, because if you do Hough transform, you need to have the space with the. Basically, you have a Hough transform matrix has the dimension contain the width and the height as as the length of the 2 dimensions, and also the radius as the 3rd dimension, right? So if you have like this original image is, I think it's like 1,000 by something, then you have the matrix space is something like 1,000 by 1,000 and 1,000. It's like pretty big. So therefore, like what I did here, I first downsample it, like just resize the image, and then afterward, like just use Cannon detector, edge detector again, like to capture this edges here. And then like I have my Hough transform exactly implemented as like what I described earlier. If I want it, it will take like actually I may want it, but it will take a minute or something. Let's see. So here like I randomly pick 2 points here, and I downsample it like instead of like, because if you think of like you have all these non-zero pixels in the image, and if you want to find all the combinations of picking like 2 of the points, then there will be like NC2 like n choose 2 so many points, right? And like typically you don't really need to try all the combinations basically. And here I only try like 1,000 of 1/1,000 of all the possible combinations. And as you can see, like the result is still kind of okay. It didn't pick out all the circles here, like it picked some of the circles here, and probably if you fine tune a little bit, you will be able to pick up all the circles. And this is my short presentation for Hough transforms. Like, do you guys have any questions? Like.